what we're going to do eventually is we're going to prove that even in this case, let's actually just jump ahead and spoil what we're doing. We're going to prove it that we can evaluate this model in d times m time, which, similar to in the previous paper, this was n times, n times k? It doesn't really matter, but basically this, the computational complexity of this model is exactly what it was claimed to be in the previous paper. However, here we have to do a bit more work to actually prove this. And so let's actually see like why this is the case. So in order to prove this complexity, we define this, they call it an ANOVA kernel, and I'm sure there's a really good reason this name comes from ANOVA decompositions of functions, which I don't know what that is, but I've heard it, and it's defined like this. And so basically this is just this is like the sums, so you give it a degree and you give it a two vectors, the p and the x. And basically you're just summing over all sequences of m integers from 1 to d of the product of all of the p's and all of the x coordinates that correspond with the indices that you're summing over. Okay, so this looks like stuff that we've seen before. For m equals 0 and m equals 1, they have the definitions like so, and so these will, this will like match up with here, and like this will match with here so that it makes sense, I believe. No, I think it comes in later. But anyways, then it is shown that this equation holds. And when they say it is shown, they mean you show it. So you need to prove this. Here where PST is the S column of PT. So that sort of makes sense with the notation from earlier, where lowercase p sub s was the S column of uppercase P. Okay, so basically what we're claiming is that the formula from 3 is identical to the formula from 6. All right, so now we need to prove that this is the case. All right, so here, let's look at the, let's choose some, so this is a sum, let's see, we've got K2, this goes up, we're taking the sum over all of these degrees here, so let's choose a particular degree. I'll just choose degree m, just because that's how I have it written in my notes. But basically what I'm going to show is that this term here is equal to this term here. And because m is arbitrary, that will show that the entire sums are equal. And so then equation 3 is equal to equation 6. So let's start with this term here. So we have the sum from s equals 1 to k sub m, doing am of p s m. It is a little confusing because I don't have a way to bold my lowercase p's. So basically, if p has a single subscript, if p has a single subscript, then it's going to be a vector. Okay, So we have this thing that we want to evaluate. So let's just use the definition. This is equal to the sum from s equals 1. Let's do it on a new line just in case. I think I'll have enough room, but it doesn't hurt to be safe. Sum from s equals 1 all the way up to k sub m. Then this thing we replace with the sum from over all jm greater than j1, product from t equals 1 to m, p s m jt. So this is the jt, just to make my notation a little clearer, this is the jt entry of the this is the JT entry of PS M, right? And then we have X, J, T. All right, yeah, and that matches, we're just using equation 5 here. All right, so now this is equal to, what is this equal to? I'm gonna skip a few more lines here. So this is, now we can bring, all right, let's write this out a little bit. Yeah, we're basically able to bring this sum inside here, and it can go past here and it can go past here. So we have the sum from over all jm greater than j1. Then we have this product. And let's just separate out the xj's because we can do that. The xjt does not depend on s, so we can bring it out. But we have the sum from s equals 1 to km. And now we have the product here, again from t equals 1 to m, of ps jtm. Because really, you could write this as the product from 1 to m of the p's times the product from 1 to m of the x's, and then you just bring this summation next to the p's and move the x's out because they don't depend on s. Okay, but so this is p sub s evaluated at jt. So this is in the vector capital P, this is the S column and the JT row. So we could actually write this, if we wanted to write this in terms of the rows of P, this is the JT row and the S column. All right, and so then what is this thing? This sum, have we seen this sum anywhere before? We should have. I believe we saw it right up here. And we saw that this sum is exactly equal to this inner product thingy. And so this becomes the sum from jm greater than j1, the product from t equals 1 to m of xjt. Then we have this inner product thing of pj1 m all the way to pjm m. And this is exactly this term in equation 3. The only difference is here I have this in product notation, and here they actually wrote it out. And they put it on the other side of this, but you know, multiplication is commutative, so that doesn't matter. Okay, so this matches. So this confirms that equation 6, this is indeed a different way of writing equation 3. Now we also need a property of this ANOVA kernel, and they refer to as multilinearity. And here they're again using really nice notation. So we have this P subset not J. Because if you, I think this appears sometimes in like propositional logic. This symbol, basically, this is like the not symbol. So P not J denotes the d minus 1 dimensional vector Pj, or the d minus 1 dimensional vector P with entry Pj removed. So basically you're taking this vector and you're removing the jth entry. So it's everything in P that is not the jth entry, and so this notation makes great sense. Okay. But anyways, we have this interesting property here of basically writing this AMPX can be written using AM of smaller vectors plus this times AM minus 1 evaluated at the smaller vectors as well. So basically you can evaluate this using smaller vectors. And this ends up being really useful. But for now, our main thing is that we have to actually confirm that this is true. All right, so let's start with the more complicated thing and simplify. So AM P not J, X not J. Ugh, these not symbols are going to be difficult to write though, but it'll be fine. Plus PJ, XJ. This is a little annoying with the lack of bolds, but hopefully it will be clear from context which one I'm using. P not J, X not J. Okay, so what is this equal to? This is equal to the sum over all Jm greater than J1. Okay, now here this is a little tricky. So P not J and X not J are d minus 1 dimensional vectors. So Jm through J1 have to belong to the integers between 1 and d minus 1. Which again, I'm using this bracket note, or this square bracket notation here, which I love. But basically these indices, none of these, well, it would have to be Jm because they're decreasing, but Jm cannot equal to d. They have to, it can only go up to d minus 1 because these are vectors of length d minus 1. All right, and then we have everything else. We have the product from t equals 1 to m of xjt times p not j evaluated at jt. All right, that's just by the definition. XJT, so this is XJT. Do we have to specify that this is X not J? In fact, do we need to specify that this is P not J either? Yes, I think so. This is really tricky because basically, yeah, J1 through Jm are integers between 1 and d minus 1. Yeah, I think these need to be, I think this needs to be X, because it's sort of like when we remove that index, when we remove the jth entry, we sort of like end up reordering, or we're sort of re-indexing the vector, and so that makes things confusing. So this is G or X not J evaluated at JT, and P not J also evaluated at JT. Again, that not symbol is not easy to write. Then we're going to add to this pj, xj times, and now we do the am minus 1 thing. So now we have the sum, and here we're taking the sum from jm minus 1 all the way up to j1, also in integers between 1 and d minus 1. Because remember, this is, so for am, we take the sum over m, we have m j's in this sum. So here we have to have m j's in this sum because it's am. Here, this is am minus 1, so we need to have m minus 1 j's in this sum. And then we have the product from t equals 1, and we're only going up to m minus 1. And now this is going to be x without j, evaluate at jt, and then p without j, evaluate at jt. Okay. So now this is equal to, and here we're going to do some reordering, or we're going to actually do some reindexing. So here we're going to take, instead of summing over indices between 1 and d minus 1, we're going to sum over all indices between 1 and d, but remove the index j. And so now we're taking the product not over x not j, but just over x itself. xjt, pjt. And why does this work? Basically, we're basically just reindexing. So here we considered x naught j and p naught j as their own separate vectors. And this sum needs to be taken over all of their possible indices. But here we're just we're allowing these j's to go up to d, but not include this j. And so that allows us to use the original vectors x and p, but we know that we're not going to run into any. In this sum, we never see the index. We never see the index j, and so we enforce that here by removing it from this sum. All right, so this sum is equal to this sum, and now let's do the same thing here. So we're going to add the sum. Now, again, we have jm minus 1 going to j1, and these are in, again, d without j. And let's see, we're going to bring this xj and isolate it. And why are we isolating this? Let me just confirm something. Let me just think about this. So let me write it out first. Xj product from t equals 1 to m minus 1 xjt times pj product t equals 1 m minus 1 pjt. All right. So basically what's happening here, oh right, of course, because we put the the pj and the xj are out front already. So now we're just bringing them inside. And we're again doing the same thing where we reorder these indices, or we reindex in such a way that instead of going up to d minus 1, we go all the way up to d, but we just make sure that we're not including j. All right, so now this is equal to the sum, and this next step might be not necessary, but I'm going to include it anyways. So it's this thing, so let me just copy and paste this. No. I'll try one more time. No, okay. It's this sum t equals 1 to m xjt pjt. So it's this plus this other thing. So now for this additional sum here, we're taking this sum, this is the sum overall. Here we're going to take jm greater than all the way to j1. This is in the integers from 1 to d, such that sum jk is equal to j of the product from t equals 1 all the way up to m of xjt pjt. Okay, so why is this true? Because if we look, basically we're just changing this term to this term. So why are they equal? So here we've got we're looking at combinations of m-1 integers, which are between 1 and d but not equal to j. And then we multiply all the corresponding xjt's and all the corresponding pjt's, but then we also multiply xj and pj. So we could absorb the xj and pj into this into what we're summing over, so long as we specify it. So if we want xj and pj to be incorporated into these products, then we need to have an extra index here. We need to have some extra jk, which is guaranteed to be equal to j. So instead of having m-1, we're going to have m, because one of these jk's is going to become that j. And these are going to be between 1 and d, and we just emphasize that some jk must equal j. And then, because jk equals j for some jk, that's going to appear when we take this product. And so this is just sort of simplifying this part, taking the xj and the pj, moving that j index into here. Okay, but now what is this? We're taking the sum, these are two sums. The things that you're summing are identical. The only difference is, let's see, here we're summing over integer sequences j1 through jm, which are between 1 and d but do not include j. And here we're doing integer sequences of length m between 1 and d, which do include j. So if you have any integer sequence from 1 to d, it's either going to include j or it's not going to include j. So we can just write this as the entire sum over all integer sequences in d of the product from t equals 1 to m xjt pjt. And this, if you match the definition, this is literally just the definition of AM. I'll write it just so that we get closure here. This is just AMPX. So this confirms that equation 7 is true. All right, and that pretty much does it for the heavy lifting here. So let's keep going and see how we put this to use.